projects, and we'll start activity towards projects on coming Wednesday lab, and either Wednesday or Friday it would be time for you to vote what would you like to do, or at least to maybe start making some developing ideas. So in the second part of the meeting, of course, I will continue delivering the class material for academic learning, but although I'm trying to do it several years, it's always no chance to relax. I don't know about students, but I have to be on a toes, not to miss deadlines, because it's very time sensitive to complete the projects. Today I'll just overview general directions, because to my understanding, some of you already have ideas, and some of you still are looking openly on opportunities. So yeah, probably I should bring slides. I have, as you have seen, there is at least one slide with list of projects, and then it will be easier to go over. So it's my favorite subject, and I would be happy to talk about these projects instead of class materials with a lot of additional things and movies and stories. But our time is limited, and maybe we need to cooperate. If before making selection you want to hear and learn more, make a request, so that I'm not telling about everything, but navigate to some particular subject. So you see, there are about 4 chapters, and they are differing in a mindset. So the code is the same that you have already practiced and reported on the last presentations. It is the same that you have reported, that you have answered questions by submitting homeworks, thanks to those who submitted. And I want to make a comment that the assignment that you have submitted by today is an investment towards completion of your projects, because when you report anything accomplished, one needs to tell which methods did you use, and answers on those questions are literal help towards those answers. I didn't count if everyone has submitted, but it's vast majority. There is a little comment, so I'm very happy with the content, but the form can be improved. It will not affect your progress and grade towards you have submitted, but by using your today submitted homework towards the final project, it is really good to have all coding formatted in form of equations. So I saw that there were some works who did half and half, not like cream and milk, but half quotes of the codes and half of the equations. Majority did just quotes of the code, and I think there is one champion in a good sense, without irony, who did all explanations in terms of equations. So there is no way to mandate it, but it is much easier to So equations are language to communicate between scientists, especially in theory. So codes can be implemented in one or another programming language, and equations are more universal. So if you are friends with Microsoft equations, or there is another form of typing equations, LaTeX, it's helpful. It's not the subject of our class, but it's will make your work more appealing. Okay, so about 4 directions. They all use the same core, the same code, but there is a different mindset. In the first section, the coordinate on our x-axis is assumed to be a position of electron or hole. This means that we literally look on the quantum properties of electron that moves in some potential. And then potential can be atomic potentials, atoms that attract or repel electron. And we literally model like conjugated polymer or semiconductor or piece of semiconductor along one dimension, projection of electronic motion on one dimension. It is very powerful direction one can make through discoveries, and it is this first like chapter A. This direction is very easy to accept by brain because it aligns to what we were doing during the class. The section B uses the same code, but now we use same equations, same computational tools, but we think about it differently. In second chapter, our particle that is moving, it is not like electron, it is interatomic distance, right? And then the potentials, instead of being like several dips that attract electrons, like ions that attract electrons in the molecule, will be more dependence of potential energy of a bond on the bond distance. So it is very much related to the subject of harmonic oscillators that we are coming in our academic part of the lecture, right? And one can design several problems that relate to actual change of interatomic motion. In addition to small deviations from equilibrium, there are a lot of chemical problems where interatomic distances change dramatically. And as chemists, by training brain and heart, you probably immediately see that it looks a definition of chemical reaction, right? When bonds breaks or forms, interatomic distances change on a dramatic scale, and one can apply the style of thinking that Joe was reporting last Friday, when we identify along the potential reactant, barrier, product, and then we literally model how reaction coordinate, which is more general than interatomic distance, expands by going through the chemical reaction. One can model it in an oversimplified way, just with 3 flat surfaces as Joe did, or one can do it with much more details. Before we go to sections C and D, I want to attract your attention to blue highlights in this slide. So what do you see? What these blue highlights tell? Huh? Model and second Okay, so what is ab initio?
Starting from first principles.
Yes, and please raise hands if starting from the first principle answers all questions, or you want more comments. Yes, no, more comments. Okay, Wyatt agrees with first principles. Sibel didn't answer, and Nate wants more comments. So please help us.
Certain modifications have been made to certain theory over time. So we're going to be starting from like the scratch instead of the modifications. That's what ab initio means.
Okay.
Basically starting from the beginning.
Is it better, or Nate, do you want more? Okay, yeah, thank you. So basically, what Lola started telling is a subject of half-a-year course that, as we go, probably I will try to make some commercial ads and to recruit more people to this course. So it is computational modeling of reactions and materials, where instead of equations to literally model everything, one uses, I wouldn't say simpler, but more natural, more intuitive way. So one draws molecule as a spheres on the screen of computer, and then automatically it assumes that each atom has attractive potential, and then one fills it with electrons, and then one automatically computes all features of the molecule or reaction. And in each of the class of the projects, one can either guess the form of a potential which we need as an input for wave packet dynamics, or one can recruit a helper who already passed through this computational course and tell, I'll pay you by including you as a co-author, or just I'll say you big thank you. Would you compute parameters of my potential for me? Or if the helper is pause recording, resume recording. So there are several active and past attendees of this class and other class who can help if you select to do ab initio. So it is free choice when you decide, but it doesn't affect evaluation and grade in the class. But if you are thinking to eventually convert this project into something towards your research, towards I don't know, publication, thesis, or just a seed of a bigger research, ab initio is a little bit more competitive, not for the class, but for the global work, global process. Lola, you will not have help. You will do ab initio and you will help yourself by doing this part. And your advisor is informed about it. Okay. So in model, you just guess, or we discuss how to put an equation that shows where are atoms. In ab initio, you get a help of a helper who sends you a file with potential as a set of values of potential as function of coordinate. Same for the chemical reactions. So someone runs ab initio, extracts details, and gives you potential where you run, if you select this path. If not, there's like Morse potentials that 2016, the name from Netherlands, from group of Kent Rogers.
Oh,
Zach for first name, and last name. Okay, so he didn't do the ab initio, but he used like advanced equations to model interatomic distances, and it was interesting. So you may decide, and I'll share his report in this class later. Okay, and I am not putting a period after the story. So this it's only introduction. I will try to tell a little bit more about project each time we meet. So next, section C. This is, I cannot judge myself in the course, but I cannot say that it is most advanced and most competitive, but it is very intriguing, interesting, and scientifically healthy approach. And this will use slightly adjusted version of the code. It is not a major adjustment. It's a little one, but it needs more adjustments to our brain. And this section C will be part of at least 3 lectures closer to the end of the class. So I will provide background. So there are no molecules that consist of only ions, except if you doubly ionize the H2. Typically, it's both electrons and ions. There are no molecules where there are only electrons. Right? Typically, there are both ions, more than one, and electrons. And there is a simultaneous activity of both. So we have electrons that can move from one electronic state or to one spatial location to another, and we have interatomic distances that can affect. In the section A, section B, we do not have this feature. We in section A, we assume that electrons are frozen, ions are frozen, and electrons are moving. In section B, we assume that electrons adjust to any change of interatomic distance instantaneously, and we don't care about them. In section C, we will, or I'm already believing that someone will select it. Those who select this section C will deal simultaneously with electronic and nuclear degrees of freedom. Electronic degrees of freedom, nuclear degrees of freedom will be treated same as in section B, as interatomic potential, but electronic degree of freedom, because simultaneous treating of both is expensive, will be just telling either it is in ground or excited. And it will take into account the fact that ground and excited potentials can be different. So this approach is a must to those who are looking for electron transfer and photoluminescence of metal-organic complexes. So I anticipate at least 2 persons to deal with it for sure. So Adam and Lola. Sybil, you may decide if
Yeah, because it could also go that direction.
if you anticipate that something gets excited in your molecule, you may select this one. This aspect also deals very much with the one of the recent grants I got myself, and what I'm doing at my free time, or what I assume to either do myself or pay someone to do. When chemical reactions are activated by photoexcitation, and therefore upon photoexcitation things break apart. So probably there is a chance that I will be a personal helper of those who select this one, which can be done as model potentials or ab initio potentials. So section D is, I wouldn't say it is least challenging, but it is especially valuable if you are thinking about pursuing career and education. So there one can look on one can revisit Bohr model, which was fundamental for all quantum theory. And one of our lectures towards the end of the class will be revisiting Bohr model and hydrogen atom with more details. But here there is a way to look literally on the angular motion, how the electron is revolving around ion, and developing wave functions of the state and see what happens if quantization rule is broken. So, and there are several extensions of this work towards more precision and making it it can be extended. If this formulation of question is too simple, one can extend it to magnetic properties of two-dimensional material, but it is also a little variation of the code. So I think I can get overexcited and waste all of the time. So it's time to speak a little bit about actual lecture. So you do not need to do a decision right now, but I hope you got some seeds of thoughts by the time when we will be voting. And of course, I will give you a chance to vote against projects and select exam. I just foresee that it will be only confirmation towards projects, but just in case, I'll make it open. So numbers should be a little less ambitious, should like 33. We already got this equation as a little exercise last time, and I would be very happy if we arrive to this slide and this equation in the remaining 20-25 minutes. I realize that may not happen, but I'll try my best. So what is going on? And probably I'll just I'll start with giving detailed introduction, because with preparing presentations, I wouldn't be surprised if all our members and minds are wiped off. I remember, I forget what happened last night, not what happened last week. It's hard. So we are in the academic chapter related to harmonic oscillator, which models interatomic distances and few other things. We already got the eigenstates, eigenfunctions, and we've learned a new concept of ladder operators, which are expected to be helpful. At least your instructor was telling that they're helpful. If you cannot check until you try something else, but and we already got enough background for static properties. Now it is time to look into dynamics, basically to reproduce what Joe told us at the very last slide of the very last minute of our meeting on Friday, when there is a wave packet when center oscillates, right? Center behaves like a sinusoidal, but its widths may also change, as we learned in other projects. So when this problem is needed, probably I need to speak a little bit of motivation. If we all are experimental chemists who characterize materials, we do FTIR, like infrared spectra of materials, to recognize them. Like in addition to NMR, UV visible, one can also recognize which modes, which interatomic distance oscillate with certain frequencies to identify the compound. And infrared spectrum just identifies frequencies. So this, even if process of measurement uses some time dependence, the actual result is not time dependent, it's spectrum, that's it. So if you are looking only into identifying vibrations by infrared spectroscopy, this next 3 lectures can be skipped. But there are several situations where oscillations and their quantum properties literally affect outcomes of measurements, outcomes of the processes, and there are specific instruments that target time resolved and quantum properties of nuclear vibrations, molecular vibrations. So Raman gets just quantum properties, but it can be time-independent Raman. But since many things are happening on a short time, such as reactions, and there is a domain of femtosecond spectroscopy which targets on monitoring how things are developing on from femtosecond to femtosecond, and there one literally monitors how interatomic distances change over time. This is intentionally needed when we have something more than boring vibrations, when things are when bonds are being broken. So in this sense, the approach that we are getting will be very valuable as a solid reference point. So chemical reactions monitored by femtosecond spectroscopy. Another aspect when we do need these oscillations are lasers. Right now, we I don't know which word to use, boys and girls or ladies and gentlemen, but we have 50-50 right now in the class and probably online. So if I'll start speaking about laser sabers from science fiction and blasters, maybe it will appeal only to the half of the audience. But we all use laser pointers and laser technology, right? Even without lightsabers. So can you guess which active media is used in those modern lasers that can be used as a weapon, that can cut through metals on a distance? Any ideas about? Well, of course, it's not a laser class, and we didn't cover it, but you know, there are two mirrors. There is active media which amplifies light, and you can damage eye of a mammal with laser pointer, but you cannot cut steel with laser pointer, right? It's there is a like p-n junction of semiconductors, and it is very low intensity. You cannot do wonders with it. So there are ancient ruby crystal lasers, and there are gas lasers on noble gases. They all are cool, but they do not cut. For making high intensity for like industry that cuts metal, or for weapons, one needs very different active media. One of the active media are gases of molecules like carbon dioxide. But then one uses vibrational levels. So one excites nuclear vibrations and make them high amplitude, and uses their quantum properties to amplify infrared electromagnetic radiation to bring it to such intensity that can cut steel. It's not the only solution. There are some other exotic examples, for example, which are not comfortable and too dangerous. But another example, it's not for the class and for this motivation. One takes hydrogen and fluorine gases, inject them together, combust them, they explode, and it promotes this HF molecule into excited state. And in this excited state, it can amplify the light that comes through. So it's a one-time laser that can be used maybe only in space. But molecular vibrations for infrared laser, it's another area where oscillations of interatomic distances and their quantum properties are really needed. I hope it was enough as a little motivation. Okay, so what are we going to arrive? I attest, certify, promise, hope that you will believe me that concept of creation and annihilation operator is the top choice to describe these processes. And we are going to focus to target molecular oscillations with quantum features, and there is a bypass. So to arrive to description of these oscillations, I will just offer some algebraic problem, which can be offered only as a problem without explanation of what it is. But following this problem, we will later solve everything like 10 times quicker than it could be if we literally start. So the algebraic problem that later will open our eyes on molecular vibrations and their quantum properties is very similar to the way how we obtained ground state of harmonic oscillator. So in case this information did wiped off, we tried our straw man to jump lower than the ground, right? We applied annihilation operator to ground state, which should be zero as a nonsense. And this differential equation gave us the functional form of the ground state. We are going to expand this little mathematical trick and apply annihilation operator to any quantum state composed of the eigenstates of harmonic oscillator. And our goal would be to solve an eigenvalue problem. So we are looking for such class of quantum states composed of the eigenstates of harmonic oscillator, so this, which will be not changed upon activity of annihilation operator. So if this is a ground state and its eigenvalue is zero, then it is one particular example, but we are looking for broader example. Why we are looking on this class of problems if you skip math behind? I'm going to say something that I believe is valuable, and I do not have any way to request a control or put it as a part of any assignment. It's only communications. So there was one of the postulates: if we create quantum system in one of its eigenstates and we isolate system, it will stay there unchanged, right? So the only dynamics it can perform is accumulate phase and but the probability distribution will be not changed. So no matter how high we excite, if it is only one eigenstate, there will be no dynamics to observe. On the other example that we did, when remember we made a superposition of first and second ground and excited state of the particle in the box, we observed that it moves forward and backwards. So actual motion that can be projected to our human intuition happens only if we superimpose several eigenstates. Make sense? Whew. Now you have a cornerstone of our next 3-4 lectures. So the necessity to superimpose several eigenstates is what we are going to do. So we are looking for states that are superposition of eigenstates. And later on, we will see that this special class of states, which are eigenstates of annihilation operator, will show this motion that can be interpreted by human brains intuitively. And I cannot keep the intrigue. It will be oscillations. But we will get everything analytically correct without computers. It can be done. And it is one of the few problems that can be done by pen and paper. It's a rare luck. Okay, so by practicing this activity of annihilation operator onto here, it means we do not know what are those expansion coefficients C, and we do not know what is this eigenvalue mu, right? So by trying to apply this annihilation operator, we are going to find a recurrent expression. We are going to find that expansion coefficients in this solution of the lower and senior and higher order are connected to each other. They are not independent. And if you arrive to this stage, it will be really helpful towards our next meeting. Okay, so we have about 11 minutes. This image is probably not for the class, but for myself, so that I remember what I'm talking about. It summarizes what we already discussed, that we do some algebra of operators, some properties of eigenstates, and later on they will help to learn about quantized time-dependent motion in molecular vibrations. The image here is from one of the fiction history movies I saw as a child. Maybe it's a repeating pattern in West movies when a character needs to penetrate a castle during the night and hide from archers, and he's taking an anchor from a boat and throws it through the wall of the castle and then climbs there. So our attempt to find an eigenstate of annihilation operator is like an anchor that will help us to get through later. And then we will be able to practice the third way to predict future. So where one finds eigenstates, composes solution and gets observable. And to compose this solution, one needs expansion coefficients, right? So our activity is in finding this expansion coefficients, and later on we will see that those expansion coefficients that come from eigenstates of annihilation operator are exactly what we need. Whew. So the rest is just boring technical details. If you do not object about the introduction that I gave, then the rest should be just easy and can be replenished, proved, rederived if anything is missed. So we're looking for such state that is not changed upon acting on the by annihilation operator. And to practice it, we do need to plug in the definition of annihilation operator that moves eigenstate k plus 1 into eigenstate k and accumulates a factor square root of k. So basically we need to plug in this expression here. Then we will have two summations. Then we will need to identify if this Bryan-Cat vectors can give us Dirac delta, if they convert and become zero in some situations. And this Dirac delta and summation should behave like snake and mouse and disappear, and expression will be simplified. So already just by looking here, I do see that there is bra here and cat there. So likely we will have delta function of k plus 1 and n. So this was operator. And these things can be combined. The summation and coefficient can be moved away from here. And by combining these two things, we will identify that this bra times cat will be 0 anytime when these indices disagree. So only if k plus 1 equals n, or k equals n minus 1. In all other cases, it will be 0, which means out of string, we parse only one number, right? So which means we remove one of the summations. So we are going to replace either k with n minus 1 or n by k plus 1 and remove one summation. Right? So there were two summations, now there is only one. So we replaced, it was k, now it is n minus 1. It was k, it is replaced by n minus 1. So we do have two summations, two series on left and right. And they are, there is an equality sign between them, right? So in which situation two series are equal? Anyone wants to help prompt? Is the question clear or not clear, or more or less clear? Oh, not clear, Nate? Okay, I'll quickly sketch an example. Suppose I have red and blue series. So red series is a0 times x to the power 0 plus a1 times x to the power 1 plus b, not b, a2 times x squared, and so forth. And then I have blue series, which has b0 times x power 0 plus b1 x power 1 plus b2 x squared, and so forth. So in this example, our basis states, instead of this Brian cat, which are eigenstates, our basis set are polynomials. Zeros power, first power, second power. Basis functions are the same in red and blue, correct? So in which situation these two series will be equal? Right, pair in a pair. Thank you. In a pairwise, the coefficients are equal. So this is equal to this. This is equal to this. This is equal to this, right? So elements with the same value of index must be equal. Whew, great. Now we have the same summation. And it would be better to perform the comparison if there will be the same indices in basis states. So just for convenience, I probably will replace n minus 1 by another letter, m, or maybe on other page I will discover it's something different. So if m equals n minus 1, then n equals m plus 1. And n minus 1 will be replaced by m. And here is summation over m. Probably I did it just in the no, correct. I was just using, huh? Yes. And if we perform this trick, if we assume that expansion coefficients in front of the same powers must be equal, if series on left and right are equal, then from series on left we'll have mu, on series on the right we have square root of n, right? And then if we want to express upper from the lower, we can divide left and right by square root of n plus 1. So what does it mean? As soon as we know lowest coefficient C naught, C0, we can immediately find C1. As we know C1, we can find C2, and it will ramp up infinitely. So on one hand, it seems that we had complicated problem to find infinite number of expansion coefficients. But now with this recursion relation, we reduce the problem to necessity to find only one, C naught. As soon as we find C naught, we will have all others automatically. So the problem is not as complicated. And I cannot tell that it will be always in any analytical problem this way. It's just highly symmetric, pleasant problem that has solution. So we're just lucky to have it. Okay, where we are? Well, we already got what we wanted, right? This expression, and time is off. Time is out. So I suggest we are finishing the class. So everyone is welcome to disconnect. Thank you for staying. I look forward to seeing you on Wednesday. Please bring your last mathematical homework. I think it will be easier than others. And if you find it is challenging, send me an email. I'll give some suggestions. It is less time consuming with compared to what we had before. So I'll judge if you have in class grading, or if it will be, if I see that everyone is so successful, maybe I'll do it myself and we'll focus on class and project. But looking forward to see you on Wednesday. And I don't want to hold you. You have some plans. If there are questions, I'll stay here, but no necessity to adjourn is announced. Whew. Bye bye. Bye, Sylvia.